Okay, so I will start today's webinar. Today's webinar, we will discuss about evaluating and accelerating fault-tolerant quantum computing development. So I will share my schedule first. Slideshow. So I will introduce about 25 minutes the fault-tolerant quantum computing readiness evaluation framework. And then we have two distinct speakers from industry. So they will share the current state of art in fault-tolerant quantum computing. So current status, challenges, and future directions. So we have two speakers. Mirin Labidrin is a CEO and co-founder and QS. He's an expert in quantum error correction and then fault-tolerant quantum computing. And then Tamoni Pandit, he's a research scientist at BT Technical Research Center of the Finland. And then we'll have about 10-minute Q&A. Okay, so briefly, I'm not going to go detail about it, and then I'll share already my presentations. And also I shared several white papers already, so you can consult them. So the physical qubit scaling is not enough, right? So increasing physical qubit count alone cannot enable large-scale quantum computation. So quantum error correction is the foundation of FTQC. And then logical qubits become the critical computational resources. And fault tolerance logic operation enable computational scale. And end-to-end engineering challenges is waiting for the full development of the FTQC. And resource overhead and scalability are critical its challenges. And then system level readiness matters more than any single metric. So ultimate target is useful, reliable quantum computation, right? So fault-tolerant quantum computing aims to transform quantum processes from error-limited experimental system to defendable computational infrastructure capable of supporting large-scale scientific and commercial applications. Okay, so this is a recent like initiate so mission. There's a DOE Genesis mission. So it's a national force. It is like led by the Department of Energy, but it is intergovernmental collaboration participating all government entities. So it's targeting the scientifically relevant FTQC relevance. So for example, that DOA quantum genesis summary that the quantum genesis read by US Department of Energy, but is quantum computing the component of the broad genesis mission. And strategic goal is the world first scientifically relevant full tolerance quantum computing capability R&D by year 2028. So it's nearly within three years. And then so why? Because the error protects the logical computation capable of producing scientifically useful result. And then you can look at over the many other things that I summarized. That I also shared the recent summit about the intensive discussion about all the aspect of this mission. And then I just curious about what the current status, right? So I decided to develop some measure, right? So how to measure the current status, right? So we are targeting within 3 years. So we need to know about what the current status in view of the within 3 years we can develop the fully functioning faultless quantum computing. So I just developed that how to measure objectively the current status. So I developed these three layers of the index that measure the current status. So I just call it like the Fault-Tolerant Quantum Computing Readiness Evaluation Framework. So FTQC, REF. So it has a three layer, physical layer, logical layer, and software layer. So you can think about just the traditional computing, right? So it has a hardware system, software system, application layer. It's very similar. So it just measure the current state means of the how much it is ready to migrate to develop further to the fault-tolerant quantum computing. So I just developed three index. So HARI is a hardware architecture readiness index, and ECRI is error correction readiness index, and then software layer is a quantum software readiness index. So this is I developed to measure. So the core question is, can the physical quantum system be engineered and scaled? So I developed the 10 evaluation dimensions. So it can be changes depending on the like you're the expert in this field, and then you can think about it in a different way. So this is my own way. I'm trying to do more object way to evaluate the current status. So I just make 10 most key the evaluation. So this is attribute to the index. So I just developed 10 the evaluation dimensions attribute. And so for each layer has 10 these dimensions. So for logical layers, can physical errors be transformed in reliable, scalable logical computation? And the software layer, can FTQC system be practically programmed, executed, verified, and operate at scale? So this is just further down. So I share already my white paper. So it is under further developed because it's not fixed yet. I just tried that. I just very curious about to whether I can develop framework to to evaluate current status. Excuse me. Uh, can you mute, please? Who is talking? Somebody talking now, please. Who is who is
Mohammed, you're not muted.
Yeah, I make mute. Okay. Okay, so I will continue. So so I just make this free index, and then finally that integration layer can, from this free index, how can it measure current status, how evaluate, and then actually the goal is not just to measure the current status. Actually, my goal is how to help from this measurement to evaluation to you make strategically develop further to migrate to further evaluate to the evolve to the final fault-tolerant quantum computing. That's a goal. So I just to invite anyone interested in this kind of endeavor. Actually, that I need some other expert to develop this framework further, and then objectively adopted from the community. So then it will be mature, and it can be objectively evaluated, and it will be a great help. So I think that this is a valuable work for this quantum computing ecosystem. So the this one actually the my goal is to the architecture neutral. So because I will show later, we have a multiple modality different infrastructure framework. So I just I will give you like 10 modalities, and then about 40 like vendors, the hardware system to supporting this modality, but actually there are many more, right? So I just to make this as agnostic about like underlying modality, and also I want to be objective, so I want to be integrate all of the like available, publicly available information. So there can be some bias, and even if I try to object, and then some maybe some other information may be not available, right? But anyway, it's a better way. Better way is to that actually that I don't want to compare to like a modality to modality or whatever, right? I'm not interested in that or at all. Maybe there will be some way to actually that there is a pro and con depending on the modality to be like further developed as a fault-tolerant quantum computing, right? For example, the D-wave quantum, right, is specifically developed not fault-tolerant computing. It's not like other like a gateway the supercomputing, but actually recently I known that they not tried to that direction also. So, so this will be won't have any kind of like the modality or whatever will under their development. Actually, if they need the objective way to evaluate their current status and then make a strategy how to migrate from them. So I will introduce briefly about how you can do using this index. Otherwise, so this is one. So turn evaluation into acceleration roadmap, right? So I want to contribute to accelerate this full towards quantum computing. So I just give you here some detail about it, but I don't want to spend more time rather than just hear from expert about their insight, right? Because this is technical, and then I already share it, and they're still evolving. The reason I introduce is I call for participation, right? Because I have been in the 30 years in all tech industry, so I'm very like experienced this kind of work before in any industry, like any industry I was involved in emerging technologies. So I'm very expertise this kind of thing. But in the default level, I'm not a technical detail expertise, all aspects of this kind of thing. So I just coined my idea, and then I just make some framework, and I want to collaborate with other people to have interesting and to contribute. I think that this is very important. I know that this some of the, like for example U.S. government agency DARPA. They are in advanced in the like the military way science and engineering advanced, but they also like some of the initiative maybe not maybe the same thing, but they also like want to evaluate like some object way to evaluate the current like the quantum computing or something like that. So, for example, the another maybe the institution maybe not they are not working like NIH or the national like a standard kind of like institution in any country have that one. So this might be a very good like topic to collaborate and develop, and then we contribute a lot to the community. Okay, so I give you some detail. So I just using this one to evaluate my own, but I'm not saying that this is fully mature yet. So all of this engineering dimension is of mine, not from industry consensus, anything, right? Because I just suggest that this is some example that you can do this kind of thing, all right? And then I need to collaborate with more expertise to finalize what is the really objective way to measure the evaluate current state of in all different aspects, right? How to measure what is the component, blah, 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 right? So ECLI is the same thing is in the logical layer. And then I give you like a detail. So still is detailed enough for me to learn the trial learn to whether they can to evaluate the current hardware modalities. So I will show later here. So in the unified engineering, so yeah, with this one actually the convergence of all three layers, so cross-layer co-design become increasingly critical. This is a key point, right? So holistic way to develop fault-tolerant computing in view of this framework. So it enable like what the cross is each layer, and then it enable like cross layer code design become increasingly critical. This is the key that I want to contribute. And then this is the summary that what the current hardware computing ecosystem. So I just give you 11, but you can have more. So supercomputing, for example, that I'm developing with other physicists. I also major in physics, PhD physics, but actually I work with another physicist about developing another modality. Currently is underdeveloped, so maybe we further develop it will be disclosed. But anyway, so the hardware modality is superconducting, trapped ion, and many other things. So this is very familiar, right? So IBM and Google, right? Rigetti and IQM. Here is IQM from Finland and other company, right? And Atlantic company is acquired by Google. So and then trapped ion is IonQ is famous. Continuum. These two companies have recently IPO in the United States. And Cura, right, is based in Boston, spin-off from Harvard and MIT. I'm a local in Boston, so I know about. And also Pascal, very famous. Infricatunch is recent coming. PSI quantum, yeah, Janata is famous, right? So you can here is this modality is very familiar, right? And other area is emerging, and then topological is especially the micro quantum and then quantum NLN that actually that I using this one every day recently. I'm developing some automation problem, real world automation problem attacking using this one. So D-Wave and then other like Eurocore is emerging. So I just evaluate them. So I don't want to compare. So I don't want to talk much about the comparison of each vendors or each modality. And anyway, but it can be done, right? So I just show that it can be done to quantitatively evaluate current state by this index. So this is a physical architecture readiness index. So I just developed this one. And then this is the error correction readiness index. I can do that. And then this is a software, quantum software. I can do that. So I indirectly, I just analyze all vendors and some of the heat maps, something like I can do that. What with their migration or what are their maturity? All kind of you can do like this one is like McKinsey and Boston Consulting doing. You can do that in that very surface level using this index. And this is one actually that I just to give you some snapshot. Recently, IDC MarketScape, they worldwide the company vendor assessment. They just measure current status. I just curious about if I measure them in view of this is a current status, so they don't measure fault-tolerant current computing, right? So they measure but their like evaluation index maybe targets some current state of art, right? But I'm just interested in the whether in view of the full tolerance quantum computing readiness, it give you IBM still top, but the others are somewhat different views. So this is just a reference to you that this is the one in a different way to view the current status. Okay, so the key is to how to use this readiness like evaluation for the acceleration of the full-tolerance quantum computing. So we can think of where are we to what should we develop next, right? So identify critical engineering bottleneck, right? And then prioritize R&D where it has the greatest impact and convert technology roadmap into engineering roadmap and enable cost layer co-design is something like you can think about it. So this is my next webinar. So I was very curious about like in general photos kind of computing sectors, and then each country has their own way to develop evolve into the photos kind of computing. So I'm just curious about what the global ecosystem. So this will be the next topic. So if you are interested, then you can join. Okay, then I will stop here. Okay, so let me check. So where is our speaker? Okay, so we have a separate Q&A time. So maybe Tamoni, you can start, right? Because maybe we need to time to join another speaker.
Mm. Okay, then maybe,
Yeah.
yeah. But thanks for the nice talk, Alex. Yeah, so I will talk about mostly like state of the art, not too technical. It's like
Mhm.
give you the high level picture, what's going on in error corrections. Let me share my screen. Do you see my screen? Oh, just a second. Yeah. So do you also see the like this?
Yes, I can see that. Yes.
Yeah. So yeah, thanks for the invitation. So I will mostly talk about the state of the art of fault-tolerant quantum computing. So this is like the technical storyline of my talk. So I'll talk about a little bit about the threshold theorem and why QC become useful. And then I will mention some breakthrough papers by Google, IBM, and then I plan to like put some of the slides. I mean that is useful like to know or learn about these error corrections. And there are some like open source software packages that one can play with. And I will also deeply show what are the different uh, publicly available softwares. And then I will talk about this little bit about the HPC integrations, and then I will also talk about different hardware platform. I mean, you already mentioned some hardware platform, but I will talk about more on the in the context of the quantum error corrections. So essentially, like the idea of this threshold theorem is like, I mean, if you have some like error, like physical error, in your quantum computer, and if the error is below like your threshold, like and you have some threshold error, and then yeah, if you increase the code distance, like in the sense like yeah, increasing the code distance, it means like if you have a bigger system, I mean, if you have a bigger quantum computer, then you'll be able to correct this error. And what does this logical error means? Essentially, like I mean, when you are not able to correct the error, the logical error. So that's what it might mean by the term logical error. And there is this paper from Google Quantum AI and their collaborators. Well, lots of huge number of authors are there. So I think this is one of the very good papers. I mean, it's like the demonstration of this quantum error corrections below the code threshold. So here the idea is like, as I told you, like if you increase the number of the qubit, I mean, it seems little counterintuitive, like how you will reduce your error in your qubit, but I mean, what they did, so essentially, like idea is like they use some like real time decoder to understand the like in where and how the error is happening, and then they try to decode the error, like uh, they map this error as a graph problem, and they try to correct the error. So here everything is happening in real time, and I also don't understand like all the details of the paper. It's quite difficult to follow their paper. But I mean, they have their like own decoder that they develop and for this kind of purpose. And so essentially, like here you can see like this is one of the plot that I mean, if you increase the like code distance in the sense like if you increase the number of the qubits, so your error goes down. So this is actually quite good. So it gives some hints that if you increase your like number of the qubit in your quantum computer, so it will help you to reduce the error. So essentially, so yeah, this is the paper that I have shown, and actually, so it's now there is this point. So I mean, now we can actually really scales, or we can actually think to really scales our quantum computer. So this is the results from the superconducting quantum computer, like from Google, what they have, and you can check that paper, and they have also in the page about this some discussion and blog post about this paper. And so essentially like to put this paper in a safe way, yes, you can decrease your logical error as you can increase your number of qubits. But I think maybe we have to be really careful. I mean this problem has not been solved yet, like the I mean, there are some other problems in error corrections, like for examples, like logical gates. Like, I mean, this paper talk about like you can reduce the logical error of a qubit. But the next goal is you also want to implement some of your quantum gates in a logical way. So this has not been done, but there are some papers like, I mean, it's possible in theory, it's possible to do logical operations. But I mean, this is still some work in progress in this community. And also there is this magic state, and preparation of this magic state is quite expensive in terms of hardware. So this is another problem. And yeah, and also this real-time decoding, because you need to really know the error in real time, and you need to really decode. You need to really understand, like proper understand of your error, and it's also kind of really hard problem. Then there is this one more paper, like I mean the paper of the Google that I have shown. I mean, it's actually like the demonstration of the surface code. So surface code, and this is actually a LDPC code. I mean, this is a different kind of code. I mean, this is more advanced code that people nowadays working on. I mean, there are some good point about this code. For example, I mean, it reduces your number of the physical qubits. So this is quite good. For example, this is the paper from IBM. So in that case, what you need, sometimes you need, let's say, I mean, this is the array of the qubits. Sometimes you need this long distance connections. And making these long distance connections in superconducting hardware is actually quite tricky. In some points, in some cases, you can do it, but it's not all the cases. So for example, here, I mean, you can see like, I mean, they have these connections, but they don't have the other part, like this kind of connection in the other part. And this is one of the result, like essentially they are showing like, I mean, you can actually reduce, like if you run surface code, like you need this many numbers of the qubit to make this code distance 12, but using this LDPC, this kind of transversal CNOT, this is also called transversal CNOT, you can actually reduce the number of the physical qubit. And this is actually another good code. Then, I mean, I try to make something fun, like for more generic audience. So essentially, like you can think this QC as a music, like how. So essentially, like you can think all of the instrument that has been played, like in some concert, it's actually a physical qubit. But sometimes what can happen, like some of the instrument can get detuned, or it can have some error, like synchronization issue. So this is the syndrome that detect, and the conductor actually infer, okay, what's the problem is happening, like during this live concert. And then he try to or she try to fix it, and then at the end, at the end, the audience what they want, some stable melody. So you can think it's like a logical qubit. Yeah, I mean, don't take these things too seriously. It's just something for fun. Yeah. Yeah, and then I want, as I told you, like there are, I mean, as I know, like there are different open source QC resource. For example, IQM, this is Finland. I mean, they have something on, I mean, something called IQM Academy. You can find there in their webpage, and they have also some tutorial about this quantum error corrections. And this is actually very good. QC is by Austin. I think he was previously working in Google, and he really maintains his GitHub, and there is also a Google group. I mean, they do it really quite regular. Their discussions, and they put their codes. And there is this Steam, and like Steam is for surface code or repetitions code. This kind of one can play with this kind of known code in this Steam. And pi matching, and this is one of the decoder of like this Steam uses. Like it's very basic, but I think it's very useful. And there is also this Munich quantum toolkit. This is also very useful. They have this LDPC decoder. Like if somebody wants to use this LDPC decoder, they can use this Munich. And Riverland, this is a company from UK. I mean, they explicitly work on the quantum error correction software. So they have also some open source things. Yeah. So more or less these are the, I mean, as I know, like free QEC resources available. So essentially, like if somebody wants to really learn from the scratch about this QEC, so we can play with this one of these packages that you like. You can build your different circuit repetitions code or surface code or even LDPC code. Then you can simulate. You can also put some noise models. I mean, it's not the exact noise model of the hardware, but it's somehow related to, I mean, it will give you some feeling. I mean, what kind of performance one should expect from if you run in real hardware. And then you can decode like this pi matching, or there are other decoder also available like this Munich toolkit. They also provide, even Devel, and they also provide some other advanced decoding strategy. And then you can actually see how your logical error and code distance behave, like if you put some noise. And so essentially, like this is like how this works. Like essentially, like this is where I think people are working in different part of the world, like this HPC integrations in quantum error correction. So essentially, you have some syndrome bit that you are getting from your QPU, like or from your quantum computer, and then you try to like record like all the syndrome bits, and then you pass it to your GPU or CPU, depending on how big your like syndrome extraction is. And it's in the sense like if you have like a very large syndrome extraction graph, then you have to part into like GPU. And then it's essentially now this is a classical problem, like it's a classical graph problem. Like you try to find out what the errors are, and essentially this is the NP-hard problem. Like try to correct this error. Like if you have the same error here and here, X and X, then if you merge them, it will become identity. But the thing is, what is the optimal way to merge them? And why this is hard? I mean, this is hard in the sense like you have something from your QPU, then you pass it to your HPC to do this decoding, and then you need to also feed it back to the quantum computer, right? Like then you will try to put some kind of reverse logic to correct the error uh, in your in your quantum circuit or in your quantum algorithm. But the thing is this, like for examples like the superconducting hardware, they are quite fast. I mean, the operation is very fast. But this error decoding part, they are kind of slow. So I mean, once let's say, I mean, you collect the data from your quantum computer, then you give it to classical HPC, and they do something, and then you feed it back. But it can happen the error also can changes in this meantime. So this is one of the problem, like how fast you can transfer your data from your quantum computer to the classical computer. So this is one of our like current research that you asked, like what we are doing here. Yeah, so this is one of our goal, like how we can efficiently integrate the HPC with the quantum computer. I mean, I think there is two problems. Like the problem is one, of course, like in the level of the software, like how fast or how efficient you can make your a decoder um, like classical decoder or whatever. But there is also engineering problems, like how fast you can transfer your data from quantum computer to classical computer. So there is two angles. One is engineering problems, and also I think engineering problem is the major problem. Like software problem is not that problematic. In theory, it should work. But yeah, I mean, we'll see. I don't know.
Tanmay, is there any reference on this HPC integration? That is a published paper, an archive, or something that you can point to?
Um, I will look at it. I think there is a paper. Yeah, yeah, yeah. But I mean, yeah, I can try to find it out. I think this is one of the reason like why NVIDIA is giving fund to everyone, because they want to sorry, increase the efficiency of the classical computer, and at the same time they want to solve these problems. Yeah, I mean, I can link you. But
Okay,
yeah, I
thank
don't
you.
know. Yeah, I mean, I'm not that confident, but this is just I mean, idea. I know we'll see where we reach. So now this is one of the slides that I thought to put like this different QC things in different hardware. Like for example, as I already discussed, like superconducting gates are quite fast, and like for examples, but there are some kind of error. For example, this leakage error. This is one of the things we are also working on, this leakage error corrections. And there is this crosstalk error, like different qubit. They have some kind of interactions, even if you don't want any interactions. I mean, this is the one of the kind of error. And there is this wiring issue, because if you increase the number of the qubit, like this scalability, like I think yesterday there was a blog post by IBM, and they try to integrate two dilation refrigerator with the L coupler. So I think, yeah, to scale this superconducting qubits, I think one also need to do like one need to connect to different dilution refrigerator. For example, this VTT with IQM. So this is one of, I mean, this is a public news, so you can also search for it. So essentially, like idea is like they are making like two 150 qubit quantum computer, and then now they want to connect it to make it 300 qubit. Like this is the way, like at least the engineers here are thinking to scale up the things. And like for example, this there are different atomic parts, atomic quantum computer like trapped neural atom. I mean, they are actually very good in some sense. Like you don't have this connectivity problem. You can connect any qubit or any ions to any ions. And doing QAC for this kind of like for example, this LDPC code is quite quite good in trapped ions and neural atoms. So you can actually produce, like for example, I think Continuum already have some like they progress a lot in this quantum error corrections, but there are some other bottleneck. They're very slow compared to like this superconducting qubit. So this is like another trade-off, like what you want to do. Like if some experiment runs, I mean, roughly, if I remember, like 5 minutes, it can take some few days to run it trapped ion. I think there is again the trade-off between what you want. And there is also this photonic, I think Xanadu and Psi Quantum, they are quite doing well. And another problem for this photonic is this like, I mean, I think people don't know how to scale up the things. But in terms of noise, they're quite good because they are photons, so they don't talk with each other. So they don't have this crosstalk and all these things. They're kind of stable qubits. But the scaling is one of the issue. I mean, I am not expert of photonic, but this is the thing I like vaguely know. And there is this spin one. I mean, spin qubit. I mean, there are some progress like in the spin, but again, there are some really like lots of engineering problems, like how to fabricate or what kind of material I wanted to choose. Again, some material science problems. So this is more or less the I mean, roughly the current status of this QVC in different kind of hardware. And okay, I mean, maybe this is some good paper if somebody wants to know or wants to learn about quantum error correction. So this Google paper and this IBM, and then yeah, like this is the paper. I mean, I can share this presentation with Alex later. Like, yeah. And so basically for the QC beginners, I mean, it could be maybe it's a good idea like to and you make your qubits and you choose what kind of code or error corrections code you want to run. And then you do some stabilizer measurement, and you can choose surface code. And then I mean, surface code is very easy to do in Steam. Then you can use some decoding strategy to understand. And there are some other methods like this lattice surgery, like this is well maintained by TQVC by Austin. I mean, they maintain really good. And there are some advanced, like as I told you, this QLDPC code and bosonic codes. This QLDPC things is kind of is possible to do like in this Munich toolkit. I have used it. But the thing is, there is another problem. Like if you want to look in general, like you do some syndrome measurement to understand the error, like you do some two qubit entangling operations. But if somebody wants to understand, let's say if I really want to do in hardware, like this kind of measurement is also noisy, right? So if I want to get that feeling in my simulation, then I need to put the error even in the syndrome extraction. So if somebody wants to do this thing, I mean, I think I don't know either. I mean, it's not implemented. Somebody has to do on top of it. So yeah, so what remain unsolved, I think, even if like this Google paper that I started my discussion, like it gives really good hint that if we scale up the things, we'll reduce the error. But there are some issue, for example, this error that is really unavoidable. And I mean, ICAM has some paper, like recent papers, like they are also working in very fundamental level, like very engineering problems. They are um, try to make their gate better. Like they are having some strategy, like how, like in sense, like you send some pulse, right? I mean, this quantum gates is very abstract thing. It's like a computer science of physicist angle of view. But in general, this is very engineering problems. You send some pulse in your hardware or atomic wave generator. So what kind of pulse one really need to send to reduce the error? I mean, IBM has also some good paper, but right now it's not that public news what kind of pulse they use. I mean, yeah, I mean, of course they have some, I believe, a smart strategy. And also like this real-time decoding is one of the problem. I think it's a software problem, like how fast you pass your data from classical to quantum, and this cryogenic control, and this is another like engineering problems. How you I mean, because you need to really cool down your system, right? Like around 8 millikelvin or 6 millikelvin. I mean, the lower the temperature is good for your, at least for superconducting quantum computer. But if you really scale up the things, I mean, you see like you have lots of wiring. So essentially it will heat up your system. So there is this another problem, like how you will do this integration. Like for example, this 3D integration things, 3D integration things some companies are working on. Like how to do this 3D integrations. Maybe it can reduce the number of the wirings. But this is the thing still not clear. I mean, it's an ongoing process.
One quick question, Tanmay,
Yeah.
if you
Sure.
can. So in resource overhead, these many qubits are required, that understand. For magic states, however, is it only corresponding to T gates, or do you need magic gates for something else as well?
I mean, magic gates like single qubit gates is a ticket, but there are also like two qubit gate. That is, for example, if you look at these IBM architectures, I mean, they have a two qubit magic gate.
Okay.
Uh,
But
I mean,
but
why they
is that
use it? I
required?
mean, yeah, I mean, IBM has a paper. I mean, you can read about it. I mean, if you use like a non-Clifford gate, I mean, then you can actually like reduce the error. So this is one of the point in terms of hardware. But in terms of software, if you want to do really like if in future if you really want to show quantum supremacy or real use of quantum computer, you need to have magic state. This is by theorem like this.
Yeah, I understand that. So, my question is if you want to do universal quantum computing, then Clifford plus non-Clifford you need to do, and the non-Clifford part is where the magic state is required, correct?
Right. Yeah.
And and the if my understanding is correct, the usual way of doing non-Clifford gate is just T gate.
Yeah. I mean, this is a simple way, but this is no. I
Yeah,
mean, there are other way also. So,
otherwise also
like yes,
including.
two qubit. I mean, this magic state. You can have a two qubit magic state, multi-qubit
Mhm.
magic state. You can always have it. Yeah. But it's also expensive, like to prepare
Yeah, of course.
tickets. Yeah. And it's
Okay,
not
so two qubit magic gate, magic state is required for what kind of non-Clifford gate?
like if you take CG, I mean, it's like a group theoretic thing. CG pi over four.
Okay,
Uh,
that
it's
controls
not
it.
good. Yeah,
Okay,
yeah,
all right,
yeah,
thank you.
yeah. So essentially, like this is like more or less the thing I discussed, like this threshold theorem of the paper from Google and Google AI. So this QLDC, LDPC code or GKP, even GKP code. So these are quite good in terms of reducing the number of the physical qubit, but there are some problems like how to connect or making all-to-all even connectivity, even in superconducting hardware. So people are actually working on it. How do we make long distance gate in superconducting qubits? And HPC integrations, yes, and different hardware has their own benefit as well as their own bottleneck. And yeah, so one can really go into this freely available QC packages that exist and can play around and can learn about this different QC code. So with that, I want to thank you for your attention.
Thank you
This is
so
by the way, this
much.
is our quantum computer.
Yeah. Oh, nice. Okay.
Yeah, I mean, find it
Yeah, we have a
in.
separate Q&A, so we can have a question and then we can have a time. Also, you can leave your question in chat box. So maybe someone maybe answer to your question. Okay, so next, Nathan, are you there?
Yes.
Oh yeah, finally. Yeah. How was your travel? Right? Because I just worry about whether you can make today.
Yeah, so an unavoidable meeting just came right before the meeting,
Uh-huh.
this one, and so but I then looked at your schedule and saw that I'm scheduled at 9:30, so I quickly joined after the meeting.
Okay. Anyway, thanks. Yeah.
Um,
Yeah.
it's great to have thank you for organizing this. Thank you, Alex. for setting up this discussion, and hope you have been having a fun discussion on the state of the art, or state of quantum, I guess, right?
Yes, yes, yes.
And thanks Tanmay for a very enlightening overview, and also your thoughts about how QEC is evolving. And also thanks to everyone for joining this discussion. So let me give you a brief introduction of myself, and then we can I'll say what I think of what and how to evaluate QEC, and also how to how to measure the progress of QEC along the way, and what are the challenges. So I'm Nitin Ravindran. I'm the CEO and co-founder of QEC Labs. I'm also a research professor at the University of Arizona. And my background is in quantum error correcting codes, decoders, LDPC codes, both on the classical side and the quantum side, and also on hardware systems required to build and run these error correction in real time. So this very much focuses on the later part of my research has always focused on the later part of what Tanmay has said about like QLDPC codes and the current state-of-the-art codes which people are actively investigating in multiple modality of qubits. So yeah, so the field has definitely made significant progress. Like there's experiments in different sizes. I was thinking when I was starting my PhD, there were experiments with 2 qubit gates, and also small, like very small surface Steen code experiments, which is demonstrated in lab. And then the repeated error correction threshold behavior, which Tanmay talked about the Google experiment. Then came the logical gate operations. We are able to now do fault-tolerant logic operations, magic state preparation, cultivation, and preparation, distillation, cultivation. There's a sequence of work on that. And of course, early demonstration in multiple modality of qubits, so error correction and logical qubits. The number of logical qubits which we can play around with in experiments, or also in these quantum systems, is increasing day by day. And every company, almost every company in their roadmaps have, um, I would roughly say 2030 or 2031, where you have truly useful logical qubit numbers. So this is excellent, and I believe there is a lot of challenges also comes with the scaling up of number of qubits. And so I would want to take that back out, saying, currently we do not have any useful and large scale fault tolerance system, right? So, but the individual ingredients which is required for making that happen, that is coming up very quickly. And the goal of our company, and also many other companies, is to like put these operations together and help everybody together to have this sort of realistic goal. So I think that's very clear distinction of where the readiness and how do you. So I think Alex might have talked. I did look at your the presentation or the long document which you send, and I really saw this tools to evaluate readiness. I would like to talk to you more about it at a later stage, or even look at the your presentation again. But yeah, so this distinction of to have everybody sort of working continuously, and also like evaluate this readiness, you need to look at all these components sort of like in conjunction or together. And yeah, so I all strongly believe that it's mostly an end-to-end like we need to prepare logical qubits, like build systems which has good logical qubits, and then be able to do computation and algorithms, useful algorithms with them. Only then we really have a truly useful quantum computer. So this is basically an end-to-end systems problem, and that's exactly. And we as a company, QEC Labs, is focused on the error correction part of it. And what we really focus in our company is to build on these systems, connecting these hardware error correcting codes with low latency classical decoding. So, and we are now sort of bridging the QPU, the quantum computing hardware, and also the control stack by using this QEC layer, which we can do very well. And so the takeaway from my initial experience with like QEC, and also working now with companies, and also hardware partners and academic partners, is that this pipeline of having a code It's like Tanmay mentioned, surface codes, QLDPC codes, or even like now there are mid-size or small-size QLDPC codes coming up for quantum computing, quantum resources, and these are all like sort of integrated. So the code, the decoders, we saw pi matching, QLDPC, belief propagation decoders, and so on. The hardware for it, whether it's QPU, the CPU, or even like an FPGA or an ASIC, and the control systems, we talked about how to take out this signals from the quantum computer and sort of like interact with the quantum computer. All these systems have to be sort of designed in cohesion. So that's really important, and even the evaluation of readiness has to be done sort of like in that with all these parameters sort of together. Um, what else? I want to sort of like spend a little bit time of what our company does, and we are really focusing on the state-of-the-art codes called QLDPC codes. QLDPC codes really, it's a I want to say that it is one of the most famous codes in the classical arena. So, for example, our 5G internet phones has the QLDPC LDPC codes as the standards. And so those LDPC codes are large in length. So number of bits which is sort of encoded in there is quite large. These are very high rate codes. So LDPC codes, there's a lot of literature on classical error correction, and in comparison, the quantum LDPC codes started maybe, and the really active work started maybe 5 years back. And we bring our expertise also from the classical world, and sort of like bring like sort of together with the quantum experience we now know exactly how to build these codes. We know how to build decoders for that. So that's the sort of experience which we bring, and that sort of gives us a unique advantage to doing error correction in this space. The other part which I would like to focus is the construction of novel QLDPC codes. So Tanmay in his previous presentation mentioned that there is a requirement of long-range connectivity, which will like help us to build these. So there are certain build these new class of codes. So, for example, superconducting qubits, when you think about Google's superconducting qubits, is more like a lattice. So every qubit is connected to its nearest neighbors. There is no far range connectivity. But like the advancements in the code sort of informed, I would say, the hardware that, okay, you cannot really restrict yourself to this nice 2D topological layout. You need to be able to engineer some far-ranging connectivity. So IBM came up with this nice architecture where you can add two additional connections, two additional far range connections, say beyond this nearest neighbor connectivity. That itself got 10x overhead reduction in terms of the number of qubits. For example, if I could use a 10,000 1,000 qubits, 1,000 uh, physical qubits, giving rise to one logical qubits, now I could move that needle down to just 100 qubits to bring out, say, 10 qubits. So that's almost like 100x like improvement right there. So you see how much like a small change in terms of how to engineer some hardware connectivity helped in reduction of the number of qubit overhead. But the state of technology, or the research went ahead, and now this 10x improvement in reduction, 10x or sort of like in improvement in overhead is now shifted to 50x. So for example, now there are ultra high rate codes. I would still not call it ultra high rate code, that's what it's called, but I would still say it's very high rate codes which can now have like an encoding capability. That is, I can take 50 qubits and sort of 50 qubits and still carve out 25 useful logical qubits out of that. So that's like you only spend half the amount of qubits as redundant qubits or for error correction. So this is a significant improvement. That means your qubit resources are precious and you're able to use them very uh, in a very nice way, without too much overhead. I just want to put that in context now to classical error correction, where we have really high rate codes, and that those high rate codes are with very minimal overhead of, like, say, zero point 0.1 or something like that. So the high rate of these codes are 0.9, 0.85, and so on. So I mean, I hope like quantum error correction codes also go that trajectory and we find better and better codes. But as in the previous speaker said, there is a lot of challenge coming up with those high rate codes as well. The decoding is much harder problem, and we need to really like investigate how to build this decoding algorithm which are fast and also reliable at the same time. So that's where we come in and we build these extra ultra fast decoders which can really push the needle in terms of the latency which you spend for classical error correction. For classical error correction, I mean, like classical problem of error correction for quantum computers should not overwhelm the computation which is a quantum computer is doing. So that's exactly what is needed for pushing that needle both on the code design part and the decoder part. And there is definitely a lot of resources which people like Tanmay pointed out, resources of how to do these error correction in a how to play around with it. And there's a lot of resources in this active. It's a very active space, and it's even harder to sort of uh, go over all the papers which come up every day on quantum error correction these days. But of course, real engineering challenges remain, and that's exactly what we should be focused on doing as a community. As a resource, as the field is growing, there'll be more brilliant ideas coming in, merging a lot of innovative results from classical error correction to quantum space will also give a lot of new fresh air, if I may say, to the thinking which this whole field has been doing for 100 years. Will also bring a lot of new innovative ideas. And yeah, as I said, like more people involved in this research will bring out the best and will sort of propel the results very fast. Um, Maybe I wind up my thoughts with some sort of like points, maybe which I would like to see. There will be definitely more experiments going from logical memory experiments right now, which is happening, to more logical circuit experiments that actually we are doing some computations. There will be more logical operation results coming up in hardware roadmaps as well. I still think surface codes will remain important in some sense, but the high rate codes will will receive much more attention, experimental attention, and also important demonstrations will happen in the near future. Neutral atom platforms being one of the major propellants for that. And so let me say in this way that the next decade of for quantum would be a big transition from, say, very isolated fault-tolerant demonstrations to sort of integrated and integrated logical computations systems. So this will of course come with a lot of efforts and investment from different organizations, companies, big and large companies, and small companies like us as well. And all these will like sort of build this cohesive environment where you can connect really good qubits, physical qubits, with really hardware-aware, very good codes which we design, and also our decoders sort of come in and resolve this problem of error correction, and we have reliable logical qubits. And this essentially will be able to do all the promises that quantum systems promise to the world. Thank you.
Thank you, Ritin. Great insight. Okay, so first we'll look at the first something which is actually the Tamoy. There are several people request your presentation, so I have a email list of all the participants. So after webinar, if you share your presentation in PDF format to me,
Yeah,
and
maybe
then
I
I
can
will
share you.
share the presentation with all participants. Okay.
Sure. Mm.
Okay, so the other thing is this is my proposal, Nathan, and then Tanmoy, because you're sort of the in between the industry and academic. I think that you know that I'm also before I was a professor at the university, so I have a also like government officer when I was in South Korea. So I've been in the hybrid or the different area. So that's why I'm very good at to find out a good topic for research, right? I was when I was a government, I was provide the fund to the innovators, and then I was academic actually. That I asked to my government officer to provide the fund, right? And the industry, I asked about venture capital. So for this kind of like fault-tolerant kind of computing is a very hot topic, right? And then this is so big, so I was find out well I can find a good fit into my expertise and experience to do something. I think that this readiness index is good topic, right? You see that, right? It's a very good topic. Then and every layers of the government and the industry, academic can want to do this kind of thing, right? So maybe anything you are in the currently in the university and also the time where you were in the like some the kind of laboratory, right? 'Cause, so how about we can free to get together, join, and then think about how make this as some project, right? And then maybe we can submit to the some of the proposal to the government or the some of the like a big company,
Yeah,
right?
this is
A little bit fun, and then we'll learn a lot, right? Because especially I'm very good at because I'm not like a deep level like engineering like a depths like you, both of you. You are the better. I did my PhD more than 30 years ago. So, but I was in industry and all of the emerging technologies, all different high-tech, deep tech. So I'm very good sense of in integration, like holistic view. And then you guys are in the very deep level understanding. So we can get together to make a good like a topic this and then we set up some initial framework and then some initial tests, right? Somebody asked about the pi quantums, like what is index like? I did, but I the reason that I don't want to be too much specific is because of the my framework is not ready yet to disclose fully because it's
okay.
experimental. I just experiment whether I can do, right? But I show that it can do. It's beautiful, right? Because it can give some the quantitative way. But because if I do something that I'm fully like sure that my evaluation, my framework is completely objective way, and then it's good enough, right? Otherwise, actually, I can get a complaint from some specific company if I do some specific about it, right? So I hesitate to do like I did this, but I don't want to be specific about compared to this company or something like that, right? Because that's why that I can do all the 40 that I design it, but I think about if too much detail, right? Because I will have a good, maybe good to show something, but if I have been in a risk to like some attack from some individual company. So are you sure that this is correct one, right? Because I sure initially then there was some complaint of some company to other company like some other different aspect, right? So, but anyway, this will be really good topic, right? As a research and experiment, and then it really have the community, right? So I don't want to be. So we are not targeting like a comparison. Right? It's compared to one vendor to other vendor, one modality other vendor, right? Because is in a concept like a collaborative they should to develop further, right? You can discuss the current computing ecosystem, right? Is diverse, right? And so we need to develop, right? Because and then another my view. This is another my view. I share my idea is because recently I'm experimenting over like a real world quantum application, solving some specific modality, right? Because I'm working on the like a T-wave is very good at optimization and other modality for the simulation, the gateway like a supercomputer. So but I'm also doing is like what you have experienced now. You think about it is the development of the computer, right? the initially like mainframe, PC, XD, like I'm with the mainframe starting my like university. I have a punch card put in the mainframe as I university. And then I go over more now supercomputer, right? And then you can think about now that the initially like this computing system drive, but now which one drive? AI, right? Application drive, right? So that's why I'm trying to like initially we targeting in the future will be the like for example I just coined the term AI enabled quantum computing. So what's the purpose of this one? Like it's a fantastic computing, right? Is like fantastic technology. No, it's we want to contribute to real life problem solving, right? Because we apply AI, quantum, other computing for what, right? Business, science, engineering, application, right? So that's what I'm now trying to do that, and then we need to be think about like it end up being that like in 3 years later, we are not just to like a fantastically working hardware system, but also like with a co-develop of the this application layer, right? So that's one should be co-developed, right? That's one I'm talking I'm really doing now. So I'm spending a lot of time every day actually testing this hardware system to whether the what's the best way to developing hardware system to apply the quantum application, right? So I just make like a top down and then bottom up, right? So the currently I'm thinking of bottom up. For example, that I saw that every ecosystem, for example, every like Continuum, like whatever IQM and other company driving their ecosystem, right? And then they starting from the like hardware QPU, and then at the end of the application, I saw that recently D-Wave like a submit. Actually, there was the article in the Nature that that's exactly what I'm doing now is that they developing their computer, but actually the in the town layer AI look at the problem and then understand the problem and then try to find out the best way to utilize their quantum computing based on their application. And they did the experiment and then that was very similar what I'm doing. I'm attacking real life problem that way. So in the fault-tolerant computing will be the that co-evolution of the AI layer and the quantum computing layer, right? That's the way actually that we can have a maximum from this one, right? And then accelerate. That's what I'm thinking about. So okay, so let's just see the what are the anything is there any specific problem or anything that you want to share or
Um,
can comment anything, right?
Uh, so Alex, I have sort of short time, but I saw a question from
Hmm.
Sahar
Hmm.
on that, so maybe I answer that first,
Hmm.
uh, just to like give my perspective in there.
Hmm.
So first question, it was about the perspective on emerging multi-core and distributed architectures to scale QPUs, and how it will impact the development and integration of QC protocols. Yes, Sahar, it's a very good question. And I think it is also very important to have this sort of scalable systems. And as you might think like it's really hard to package and integrate a lot of wires on one system. And people are definitely thinking of distributed computing and distributed systems, sort of like you know, it gives new challenges to QC, that we have to now work with small systems, but then you need to have like sort of these paired shared resources, bell states essentially to link to the next system, and how well we can really do sort of like logical operations on one block and then logical operation on the other block, and how do you do it seamlessly in distributed manner. So this is very active topic, and for example there are like recent papers coming up, what is the whether we should do like distributed computing using Bell states or using Bell measurements. So there are nice papers coming up on the resource overhead, resources on that. um, even in the photonic architecture, photons can also be used to this for this distributed computing aspect, or distributed um, resource generation and resource sharing aspect. So there is nice works on that as well. The other part I would like to talk a little bit more is maybe This also would be great to scale qubits QPUs with heterogeneous systems. Like there is this DARPA's project which is happening right now, and Arizona is also part of one of them. University of Arizona, and my colleague is actually part of one of the HARQ programs, HARQ. So if you Google, I think you can find the resources and what are the active topics on that. It's one of the important challenges to how to sort of integrate different heterogeneous systems in together, and this also talks in the same line of scaling up systems. So there are if for example I can think of QEC, which is so as a memory you can use very high rate codes, and then now for a different system with where you do say you do computation, you can use different code system itself, which is amenable to for more computation aspects. So there's definitely a lot of interesting questions there.
Thank you. Any
And
other things to comment or anything? Okay.
so I think there's great. Yeah. So like I can put my LinkedIn in the chat so that if you guys want to connect with me on LinkedIn, and I can if I have more resources to share, I can definitely do that. Um, that's pretty much. And thanks again for to everyone for listening to us this
Yeah.
time.
Yeah.
Hopefully it was an engaging discussion, and appreciate your thoughts and comments.
Thank you.
And Alex, we'll talk more on offline about how we can also discuss these projects which you're thinking about in your what you said
Yeah.
about.
Yeah. Fantastic. Okay.
Sounds good.
Okay. So if there is any more comment or the question, then I will wrap up. Okay. Okay. So thank you for attending today's webinar. So I will share the presentation and recording with you through the LinkedIn and also in the email. Okay. I hope to see you in my next webinar. Thank you. Take care. Bye bye.